Welcome to section 7.5, write and graph exponential decay functions. Now, an exponential decay function is like an exponential growth function, except it gets smaller instead of bigger. So if you were to look at a graph, instead of an exponential growth where it starts low and then gets big fast, an exponential decay starts big and then gets smaller and approaches zero. So first thing we're going to do is just figure out, does the table represent an exponential function? Or in other words, are we multiplying by a repeated number each time? If so, then we have to find a rule for it. Well, to get from 1/9 to 1/3, we could multiply by 3. And to go from 1/3 to 1, we would multiply by 3. And to get from 1 to 3, we multiply by 3. So yeah, this does represent an exponential function. So our equation in this case would be y equals a times that repeated 3 that we multiply by to the power of x. Now, what we have to look at is what's that value of a? Well, remember, that's just the y-intercept when x is equal to 0. So in this case, that's going to be 1/3 times 3 to the x. Let's try this next one. As our x's go up by 1, to get from 4 to 1, we would divide by 4. To get from 1 to 1/4, we would divide by 4. To get from 1/4 to 1/16, we would divide by 4. Well, when we divide by 4, that's the same as multiplying by 1/4. So this is still an exponential function. We're just multiplying repeatedly by 1/4. 4 times 1/4 is 1. 1 times 1/4 is 1/4, and so on. So this is still an exponential function. So it's y equals a times 1/4 to the x. Now, again, what is our a? Well, our a is whatever the y-intercept was. So in this case, it's a 1. And now we've got our function. So let's go ahead and graph this equation quick and identify the domain and range. Again, just like last time, we're still going to have that horizontal asymptote at 0. So our domain is not affected by that at all. It's still an exponential function. There's nothing that would stop us from letting any x value work. So our domain is all real numbers. Our range, however, is going to be y is greater than 0, because we're going to stay above that x-axis. What would make it go below that x-axis would be if we had a negative out in front, but we don't. So now at this point, we can just go and graph our graph. So let's say we go for -2 up to +2. So at -2, we'll make a little xy chart. At -2, we go and do 1/2 to the -2nd, which would make us take the reciprocal and would give us a 2 squared, which is 4. And then we repeatedly multiply by 1/2. So -1, you would multiply by 1/2, and that would get us down to 2. 0, you multiply by 1/2, and that gets you down to 1. 1, you multiply by 1/2, you get down to 1/2. Oops, 1/2. And then 2, you multiply by 1/2, and you get down to 1/4. So 2, 3, 4. At -2, we go up to 4. At -1, we go up to 2. At 0, we go up to 1. At 1, we go up to 1/2. And at 2, we go up to 1/4. So you can see, even just from this, sort of what that exponential decay graph looks like. And we're going to go and do a similar situation to the last one. And we still know our answers as to what the graph of y equals 1/2 to the x looks like. So it's a 4, 2, 1, 1/2, 1/4. Now the difference when we go and we're multiplying by 3 is we do that again at the end. So 4 times 3 will get us to 12. 2 times 3 is 6. 1 times 3 is 3. 1/2 times 3, is 3/2. 1/4 times 3 is 3/4. Oh, this last one is different though. We're multiplying by -1/3. So 4 times -1/3 will be -4/3. 2 times -1/3 will be -2/3. 1 times -1/3 will be -1/3. 1/2 times negative 1/3 will be negative 1/6. And 1/4 times negative 1/3 will be negative 1/12. So now if we go ahead and just graph these, our y value has to go as high as 12 and as low as about negative 2-ish. So we're only going left 2. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We only have to go down a couple. So we can graph that first one. So that was started at 4, then went down to 2, then to 1, and then to 1/2, and then 1/4. And so that would be our original graph. We can then graph the one we multiply by 3, because that one starts at 12, and then goes down to 6, 1, 2, 3, 4, 5, 6, and then goes down to 3, and then goes up down to 3/2, and then down to 3/4. So if we do this one, that one will come in and look something like that. Now then when we multiply by that negative 1/3, that's going to end up flipping it over that x-axis. So at negative 2 will be at 4/3, or about negative 1 1/3. At negative 1 will be at negative 2/3. Then we'll be at negative 1/3. And then 1/6, or negative 1/6, and then negative 1/12. So that really flattened it out and got us really small and really close to 0 really fast. So the last thing I've got for you in this section is talk about an exponential decay model. Just like last time, the A is your starting amount, the R is your interest, or not your interest, your percent as a decimal, and your T is the number of years. The only thing that's different than the exponential growth is it's a minus this time. So instead of a 1 plus R, it's a 1 minus R. So the acres of ponderosa pine forests in the western United States decreased by 0.5% annually. In 1963, there were 41 million acres. Model this function. Well, 41 million would be our starting amount. And we'll just do this in terms of millions. And we then multiply that by 1 minus 5%, or 0.5% as a decimal is 0.005 to the t power. Well, to get from 1963 to 2002, well, let's see, 40 years would be to 2003, so that'd be 39 years. So 41 times 1 minus 0.005 to the 39th power. That's going to go ahead, and I will actually quickly switch over to a graphing calculator for this. So it was 41 times 1 minus 0.005 to the power of 39 equals 33.7. So there would be 33.7 million acres of forests left in 2002. So that's all I've got for you for today. So good luck, and